Hello. So we try to solve a couple of new examples today, but example by example, and for calculating and drawing shear force and bending moment values and diagrams for the cantilever examples. So we have this example, let's say here, draw the shear force and bending moment diagrams and label values at points of interest for the following beam or cantilever. Describe the beam's own weight where it's not given. So since the weight of the beam is not given in this problem, so we will just ignore it and we're not taking it into consideration. So step one, as we know what we do in this type of applications, we start drawing the free body diagram. So step one, it's a free body diagram for the beam. And that means we will show what will happen to the beam itself. So I will put the free body diagram on the original and just using arrows with different colors. So this will be impacted by a support reaction force going upwards. We'll make it more clear to see through. And we will give it a recognizable color to distinguish and make it clear. So make it, for example, green. And let's say this is acting on that line. Remember, even the beam looks like that one, but we need to find the center line for it. So whatever is that center line, you can see even in Word or PowerPoint is giving me the center line, which is the 2 points passing through. So let's say this is the center line for it. I'll just make it disconnected line to show you where is it going through. And this where is acting the components of force. Let's call this one as RA, support reactions at R. And also we have support reactions for cantilevers. It's acting on that direction, which we could call it, for example, R. Well, let's call it different actually, RY, this one, and the other one we call it RX. So because we have components in X and Y direction, therefore we can call each one of them in different components Rx. Now, something is new happening when you have a cantilever, which we haven't done, for example, in fixed supports or roller supports beams. You have another value, which is the moment, or how is acting that moment. So in this case, in this example, we'll assume the moment is going counterclockwise because I always solve it clockwise. So this time I want to do it something kind of different. So let's say this one. So here I put a moment is going in that direction, and I call that moment, you can call it M, for example, and depends on the location. So if that point was A, let's give it in words A, AY, and AX, and this one MA. So A should be something just as small to it to indicate we're using a moment at that point. Right, so these kind of the things is shown for a cantilever, what support reactions we're getting from it. So you have support reactions going in that way, and then in the Y direction, support reactions going in the X direction, and as well a moment going through that point. It's very easy to show these values or show the direction of the force, but definitely we're not confident if they are in the right direction if I don't do or perform my calculations, such as calculating support reactions. So when you do the free body diagram, I just draw on it, but definitely you need to remove that support reactions and you do it. And you look carefully. I started putting those points where is the location of the distance 6 meters. So this bar or beam, it has 6 meter length, and there is a 3 meters, 10 kilonewtons, another 2 meters, 5 kilonewtons, and that end is free. That's what we call it cantilever. Step 2. Step 2, we need to calculate the values for find AX and AY, and as well MA. because based on these values, we could determine all the support reactions. One interesting thing on this example, because I don't have any force in the x direction, so I need to show that by calculations. So I will type the equation, algebraic summations of forces in the x direction, f x is equals, or just make it small letter, is equals to 0. And that indicates for me, I need as well to be clear for the readers, like you need to say which direction is x is going. So I'll say this is my positive x. It's very important because I want to know what you're trying to achieve here. Then it's very good to demonstrate all the solutions. This will lead that ax is equals to 0 because there are no supports or no forces. So to be supported by x. If there were support, like if the 5 kilonewtons is inclined with an angle, definitely the AX will be active and will be doing the job. So at the moment is not active. That's the meaning for it. So that's the components in the x direction. Now, either I take the moment around point A and then I found the MA, or I could do the summation of forces in the y direction, which is the easiest one, and I can find the value for AY. So let's try to do that. So algebraic summation of forces in the y direction. I just need to use that. So Fy equals to 0. Of course, going upwards is positive, therefore AY equals to what's the remaining of the forces on the other side. So AY is going up is one force, and you have 10 plus 5, so those forces going down. And that's what leads for us, that's the force AY, or support reaction AY, is equals to 15 kilonewtons. Please don't forget the units. They are very important in our calculations. So again, to make it sure clearly why I assume this positive, I'm not going through the steps of this because we have done previous examples. You can watch them on YouTube. But just telling you everything is going upwards is positive. So AY is positive, and these ones is going downwards. So therefore, I put them negative. So they have the force in that way. So now we kind of identify AY, and also we found AX. Now I need to determine the value for MA, which is very interesting. This MA, we haven't done it before because in fixed supports or rollers, we don't have a moment, if not moment specified there. But in this kind of applications, definitely we have a moment and we need to show it. So algebraic summations of moment around point A equals to 0. And now we need to write this equation around point A, but we need to find what is equal at that moment. So actually this one, it doesn't mean it's equal to 0, but we want to find what's the moment here. So we need to determine the forces, which directions they're going, and then we assume that if it's x and y. So if I assume that direction is positive, which what I'm trying to achieve, then we need to find the answer for that. So this is my positive moment. So now I'll write the equation. I just need to remove the highlighter here so we don't have any highlights. So what do we have? If we fix a point at point A here, and we'll see that 5 kilonewtons will rotate clockwise, and the 10 kilonewtons also rotate clockwise. So that definitely they are negative forces, and the MA will rotate anti-clockwise. So if we write that equation, so it would be, we start from one of the last ends from the moment. So this ends, we're going through point A. So first one is 5, which is the force, times the distance, 3 plus 2. So here is the 2 meters plus 3 to this point, and plus what do we have is the 10 kilonewtons and the distance, which is 3 meters. So that is equals to what? Or in other words, it's minus insert the moment, which is the one we're trying to achieve here. So MA equals to 0. So that's the equilibrium for the moment. Now, if you perform this in using your calculation, so just use any normal calculator here, and then you can find the value for the values you're trying to find. So 5 times 5 is 25, plus 30, then the answer is 55. So here we just say this will lead us that MA is equals to 25. Oh, sorry, 55. And here the units is kilo newtons meters. Please pay attention for this. It's very important. Many students, they confuse that with the force, and they write only kilonewtons, which is not correct. So that's actually what we try to achieve, and when we get the answer for it, so I will highlight this again, and to say we have found the 3 support reactions, AX, AY, and MA, values for them. Now, what's interesting at this stage is we need to sketch the shear force and bending moment diagram. I will just move this dimension up, so I will have enough space to sketch my shear force diagram. Sometimes shear force diagrams and bending moment diagrams for cantilevers, they act slightly different from the other beams which fixed supports or roller supports. So we start with one end, which is the point A. At point A, what we found that AY is equals to 15 kilonewtons. So before I start there, I will sketch the points. I need to label, this is my shear force diagram. It's in kilonewtons to make sure that everyone will read there the values. And then I will sketch a line moving from this point, going straight forward to here. I'll highlight it a bit darker, and that's the value for it. It's, as we found, the AY value, it's 15 kilonewtons. I don't need to write the units again because I already labeled this diagram. Now, what's happening from this point till the 10 kilonewtons, it's almost no impact, no changes in the force. Therefore, I will continue as a flat line till I reach to the 10 kilonewtons. And then I get 10 kilonewtons. This will push me down, so going downwards. So that will be 10 minus, 15 minus 10. The remaining of that is 5. So I will stop here and will be 5. Still, we are in the positive above the line. And then I continue as well with a straight line. There is no force acting along this distance, if you can see, till I reach to the 5 kilonewtons, and therefore I need to go down again because the direction of the arrow is indicating for me the force is downwards. So when I come here, that's when it's my 0. And then I need to close that diagram for, again, if you can see, from this point till there, it's going to 0 because we don't have any force at the end of that free cantilever. So this is technically how the shear force diagram represented for cantilever. Very easy, very basic, but sometimes confuse students. All right, so just work it out in the way how you believe it works, and then you try to sketch it and see how it works. Now, what's interesting here, we found the shear force, it's giving me a positive areas. And remember, that will be very helpful for us to calculate. So this one is a positive area, and also this one is positive area until you get the 0, which is good for us because that will indicate that my bending moment diagram will be in the positive. So after step 2, we determine the shear force diagram, which is, this is step 3. Kind of will make the steps to be clear for you guys, and shear force diagram. And now we'll have a step which is number 4. So step 4 will be bending moment diagrams, and we need to change the units and the word. So BM, representing bending moment diagram, and here just we add meters. So we need to convert these rectangular shapes to slopes, as I explained in the class on Monday. And how can we find that slope? By finding the relationship between them. Now, what's interesting about cantilever, we know the value for this bending moment, which other moment is indicating for us that the bending moment here is going anti-clockwise. So I will, since I assume it that way is my bending moment, and you see the assumption is made early here, then I will follow it. So that 55, which we found our point A, will go up. So technically, I should start from a point representing the bending here, because this is the end of it. Therefore, I should come to this point and I say, I'm here. Just need to have this line straight. Make it darker so we can see, maybe different color. Make it red. Now, this is 55 kilonewtons meters. Excuse my scale, because of the limitation of the PowerPoint, I don't have enough space to do it. So I don't need to do anything here. Now, what's happened? That's the maximum bending moment, is obviously we got in this diagram. Now, I need to determine that area. So I will write the equation for bending moments on the side so you can understand how we will perform the calculations. So I have 55, which is the highest bending moment we're getting here. And then we need to indicate how much we're going in the positive direction. But what's interestingly here about cantilevers, which has confused many students, it's not adding anymore, because that's the maximum we started with. So if that one is 55, technically speaking, it's a moment going on the opposite direction, but it's giving me a value of 55. So the other area right here, it's 15 times 3. So 15 times 3, it indicates for you how much are we trying to see the difference between them. Sorry. So that is equals to 45. So now you have, this is very interesting, which I say to you guys many times. This is 55. And this one is 45. It's definitely you're not adding an extra bending moment. So it's very wrong to consider you going up. No, this is the maximum bending you will get at cantilever in this direction. That's the maximum you're trying to achieve. Therefore, you need to go down in these things. I know it's completely different. Now, many people, they explain it in negative or positive. It depends how you look into it. You could draw this and going downwards, or you could draw this going upwards. In many textbooks, what they assume that they go here and they assume this is a negative number, which is that's the indication for it. And they move that number down. And they say this is minus and the area is a plus. Therefore, you get a value as equals to what? Is equals to minus 10. And then from here, you will see that this line will move as a slope. So from this point, we'll go to around this point here, and it has the value minus 10. And then we moving as a positive, so we go back and we write the equation again based on what we learned. Minus 10 plus the area, which is for that rectangular, which is 5 times the value of 2 meters. And that will give you 10 minus 10, which is equals to 10 plus minus 10 plus 10 equals to 0. Then this one will go and continue from this point, and then we'll try to go to that line here. But then we need to connect this one a bit slightly, and then we continue with a flat as well. When there is no shear force there, it looks like there is no moment acting there. That's how the bending moment diagram representation for this kind of application is a bit slightly different from what you see in general applications. So again, because as I taught you before, maybe I need to make it this clear now for you. Even we solve the bending moments as a anti-clockwise as a positive, but still when I try to do my shear force, it's easier way for us to assume that the clockwise is a positive one. Some people, they could draw this on the opposite direction. And remember, in the bending moment, you could get the same values. So now still the maximum shear force is 15, it's happening at this point, and the maximum bending, it's 55, it's happening at this location. It's completely acting differently from shear force bending moment diagrams for normal beams. If you see in the other places where the shear force was equals to 0, you can get the maximum bending moment. But here is completely different application and different example. So that's why we need to be very careful for it. So that's how it looks like, the shear force. So if you started from that, assuming it as a negative, because we're drawing as a counterclockwise, so when we try to draw here, is clockwise what's positive. So so if we getting this one as a positive, therefore this one is also anti-clockwise, so it's minus 55, and then because of the positive area, we're subtracting and adding, so minus 55 plus the 15 times 3, and then that's negative number plus 5 times 2, and then you get the 0 and you finish that. So this is a very good example for you guys. I hope you enjoy it, and I will add another example for this topic with different scenario. Thank you very much.